Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will discuss last topic, that is partial differential equations. Let us consider first the order and degree of partial differential equations. The order of the partial differential equation, in short PDE, is the order of highest order partial derivative occurring in the equation, and degree of partial differential equation is the greatest exponent of the highest derivative occurring in the equation. For example, the equation x dy by z by dy by x plus y dy by z by dy by y equal to z is first order and first degree partial differential equation. And the equation dy by 2z by dy by x square equal to dy by z by dy by x is second order differential equation and highest order, that is 2, and its degree is 1. Another example is dy by z by dy by x bracket square plus dy by z by dy by y bracket square equal to 4z. This is first order differential equation and degree is 2. Now we consider linear and non-linear partial differential equations. A partial differential equation is said to be linear if all the derivatives in it are of first degree. For example, x dy by z by dy by x plus y dy by z by dy by y equal to z. It is first order linear differential equation. Second example is x square dy by z by dy by x plus y square dy by z by dy by y equal to z square. It is also first order linear differential equation, linear partial order differential equation. Third example is dy by 2z by dy by x square plus dy by 2z by dy by y square equal to 0. It is second order linear partial differential equation. Another example, that is fourth example, is dy by 2z by dy by x square plus 5 dy by 2z by dy by x dy by y plus dy by 2z by dy by y square equal to 0. This second order linear partial differential equation. And last equation, that is number 5, is dy by 2 omega by dy by x square plus dy by 2 omega by dy by y square plus dy by 2 omega by dy by z square equal to 1 upon a into dy by omega by dy by t. It is second order linear partial differential equation. All partial differential equations in which derivatives are not of the first degree are called as non-linear partial differential equations. For example, consider first example, dy by z by dy by x bracket square plus dy by z by dy by y bracket square equal to 1. It is first order non-linear equation. Here degree is 2. That is partial differential equation in which derivatives are not of first degree. These are non-linear partial differential equations. That means non-linear partial differential equations means degree is higher than 1. Second example is dy by 2z by dy by x square bracket square plus a dy by z by dy by x equal to dy by z by dy by t. This second order differential equation and degree is also second. Third example is dy by z by dy by x bracket square minus dy by z by dy by y bracket square equal to 4 dy by z by dy by x. It is first order and degree is 2. And it is non-linear since degree is more than 1. Now we consider classification of first order partial differential equations. Here we consider two notations like dy by z by dy by x equal to p and dy by z by dy by y equal to q. Hence dy by 2z by dy by x square here equal to r. This is one notation. And dy by 2z by dy by x dy by y equal to dy by 2z by dy by y dy by x equal to s, and dy by 2z by dy by y square equal to t. These are the notations we have assumed. In general, a first order partial differential equation is a relation symbolically written in the form as f of f into bracket x comma y comma z comma p comma q bracket complete equal to 0. First order partial differential equations can be formed in two ways: by eliminating arbitrary constant, a given relation between the variables. That means by eliminating arbitrary constants we can find first order partial differential equation. And another method is by elimination of arbitrary function of the variables we can find first order partial differential equation. Let us consider first method, elimination by arbitrary constants. Let us consider the formation of partial differential equation by elimination of arbitrary constant from the relation between the variables. Let a relation between the variables x, y, z containing two mutually independent arbitrary constants a and b be f into bracket x, y, z, a, b bracket complete equal to 0. We denote this relation as equation number 1. Differentiating this relation 1 partially with respect to x and y, we get delta z by delta x plus delta p by delta z into delta z by delta x equal to 0. That is delta f by delta x plus delta f by delta z into p equal to 0. And another equation is delta f by delta y plus delta f by delta z into delta z by delta y equal to 0. That is here delta f, that is delta f by delta x plus delta f by delta z into delta z by delta x equal to 0. That is delta f by delta x plus delta f by delta z into p. P means delta z by delta x. We have given notation here. P means delta z by delta x. Q means delta z by delta y. We have assumed these notations are ST also. From this one we can get also relation as delta f by delta y plus delta f by delta z into delta z by delta y equal to 0. That is delta f by delta y plus delta f by delta z into q. Q is delta z by delta y equal to 0. We denote these equations as equation number 2. Eliminating the arbitrary constants a and b from the relations 1 and 2, we can obtain a relation between x, y, z, p and q as f into bracket x, y, z, p, q bracket complete equal to 0. This is a partial differential equation of first order derived from the relation 1 by eliminating two mutually independent arbitrary constants a and b. Clearly, 1 is the solution of partial differential equation 3. Now we consider some remarks. First remark is the number of mutually independent arbitrary constants is equal to the number of independent arbitrary variables. That means number of mutually independent arbitrary constants is equal to number of independent variables. We obtained a unique partial differential equation of first order. Second remark is if the number of independent arbitrary constants is less than number of independent variables, we obtained a first order partial differential equation which may not be unique. And third remark is if the number of mutually independent arbitrary constants is greater than number of independent variables, we obtain a partial differential equation of higher order than 1. Now we consider some examples. Let us consider the example z equal to ax plus by plus ab. By eliminating arbitrary constant a and b, we have to solve this example. We first write given equation in this solution. Differentiating partially with respect to x and y respectively, we get del by z by del by x equal to p equal to a plus 0 plus 0. Since we have with respect to x, y is constant, a, b is constant, a is constant. So we get p equal to a. And with respect to y, we get del by z by del by y equal to q equal to 0 plus b plus 0 equal to b. Thus we get, replacing values of a and b, we get z equal to ax. Ax means a means p. Px plus b means q. Qy plus pq. This is solution of given equation. Now we consider another example. Solve in bracket x minus a bracket square plus in bracket y minus b bracket square plus z square equal to c square. We first write given equation in the solution. Differentiating the equation with respect to x and y, we get 2 into bracket x minus a bracket complete plus 2zp equal to 0. Since with respect to x, y is constant. Z is also function of x and y. So we get 2 into bracket x minus a plus 2z into del by z by del by x, that is p equal to 0, to zp equal to. Hence we get x minus a plus zp equal to 0 by cancelling 2. We denote this as equation number 1. And differentiating partially with respect to y, we get, with respect to y, x is constant. So we get 2 into bracket y minus b bracket complete plus 2zq. Since derivative of z square is 2z and del by z by del by y, that is q. 2zq equal to 0. Cancelling 2, we get y minus b plus zq equal to 0. We denote this equation as equation number 2. Putting x minus a equal to minus zp and y minus b equal to minus zq in the given equation, we get z square p square plus z square q square plus z square equal to c square. That is z square into bracket p square plus q square plus 1 bracket complete equal to c square. This is solution of given equation. Now we consider second method, that is solution of partial differential equation by elimination of arbitrary functions. Let u equal to u of xyz and v equal to v of xyz be two independent known functions of the variables x, y and z, and let f of u v equal to 0. We denote this as number 1 relation. Be an arbitrary function between u and v. Regarding z as independent variable and differentiating one partially with respect to x and y, we obtain del by f by del by u into bracket del by u by del by x plus p del by u by del by z bracket complete plus del by f by del by v into bracket del by v by del by x plus p del by v by del by x del by z bracket complete equal to 0. We denote this as equation number 2. And we get del by f by del by u with respect to y. We have to differentiate del by f by del by u into bracket del by u by del by y plus q del by u by del by z bracket complete plus del by f by del by v into bracket del by v by del by y plus q to del by v by del by z equal to 0. We denote this as equation number 3. Eliminating del by f by del by u and del by f by del by v from these equations 2 and 3, we get this determinant, that is first row is del by u by del by x plus p del by u by del by z. This is first element. Second element is del by v by del by x plus p del by v by del by z. This is first row. The second row of first element is del by u by del by y plus q del by u by del by z, and second element of second row is del by v by del by y plus q del by v by del by z. Determinant equal to 0. On expanding this determinant, we get del by u by del by y into w by z minus w by z into w by y in bracket complete into p plus in bracket w by z into w by x minus w by x into w by z bracket complete into q equal to in bracket w by x into w by y minus w by y into w by x bracket complete. Hence we get w comma v divided by y comma z into p plus w comma v upon z comma x into q equal to w comma v upon x comma y. We denote this relation as equation number 4. Writing w comma v upon y comma z equal to lambda p and w comma v upon z comma x equal to lambda q and w comma v upon x comma y equal to lambda r. Equation 4 reduces to pp plus qq equal to r, where p comma q comma r are functions of x, y and z. This is first order partial differential equation which is linear in p and q and free from the arbitrary function f. The relation 1 is a solution of equation 5. Now we consider one remark. The partial differential equation pp plus qq equal to r, it is called as Lagrange's linear equation. One can, for objective, this can be asked as Lagrange's linear equation is dash dash, that is pp plus qq equal to r, or pp plus qq equal to r. This equation is known as dash dash, that is Lagrange's linear equation. Here linearity consists only in the partial derivatives occurring linearly in the equation and not that the independent variables occurs in it. Second remark is, it is not only the Lagrange's linear equation that is obtained by eliminating of arbitrary function, but some non-linear equations can also be obtained by elimination of arbitrary function. For example, p square equal to 4. This equation can be obtained from z minus fy in bracket square equal to 4x square by eliminating an arbitrary function. And last remark is, elimination of two arbitrary functions give rise to a partial differential equation of order higher than first. These remarks can be asked for objective also. Thank you.